6.2 Retrieving entropy data. We can look up the entropy values from the thermodynamic tables, just like we did to determine the internal energy or enthalpy from the thermodynamics tables. We can determine entropy. So as the state principle describes, we need two intensive, independent properties to fix the state. So we can determine entropy from pressure and temperature. We can also determine entropy from pressure and specific volumes. Entropy can be also determined from temperature and specific volume. The entropy value is given relative to a datum, which is an arbitrary reference point. So let's take a look at the saturated water table. This is table A2. So in the thermodynamic table, the entropy of saturated liquid water at 0.01 degrees Celsius is set equal to 0. So this is an arbitrary datum. So there is no absolute value of entropy at a specific state. So instead, we are interested in the entropy change between the states. Let's work on a problem. Consider two states of water. At state 1, the pressure is 3 megapascal and the temperature is 500 degrees Celsius. We know two properties. They are intensive and independent. So we can fix the state. At state 2, pressure is 0.3 megapascal. The specific entropy is same as at state 1. So at state 2, pressure is given and the specific entropy is same as state 1. So we can fix the state. Determine the temperature at state 2. First, at state 1, pressure 3 megapascal. See table A4, pressure 3 megapascal, temperature 500 degrees Celsius. So entropy at this condition is 7.2338 kilojoule per kilogram Kelvin. At state 2, pressure is 0.3 megapascal and entropy S2 is same as the entropy at state 1, which is 7.2338 kilojoule per kilogram Kelvin. So we know two independent intensive property at state 2. So we can fix the state. So entropy 7.2338 sits between these two. So we can interpolate between these two temperatures, and T2 is calculated to be 183 degrees Celsius. If a substance is a saturated vapor and liquid mixture, we may use the quality to determine the property of the substance. So it is the same method we used to determine the internal energy and enthalpy using the quality. So the entropy is calculated using these equations, and we are going to work out this example. Determine the specific entropy of refrigerant 134A at a state where the temperature is 0 degrees Celsius and the specific internal energy is 138.43 kilojoule per kilogram. 0 degrees Celsius and the internal energy is in between these two numbers. So we know that it's saturated liquid vapor. So with a given internal energy value, we can determine the quality. So quality can be expressed for the internal energy. So internal energy for the saturated liquid internal energy for saturated vapor. So quality is determined. Now we use the quality to determine the entropy. Entropy for the saturated liquid is 0.1970. Entropy for saturated vapor, 0.9190. So we can determine entropy. So we use the same method to determine the internal energy and enthalpy using a quality. The entropy of a compressed liquid for water may be found in thermodynamics tables. If the thermodynamics tables are not available, the substance may be approximated by the saturated liquid, and we use the saturated liquid vapor table. So let's see this example. Determine the specific entropy for water at 25 bar and 200 degrees Celsius. Let's say that compressed liquid data is not available for water at this condition. So we're going to use saturated water tables to approximate by the saturated liquid. So we know the pressure and temperature, 25 bar and 200 degrees Celsius. In table A2, this is the saturation temperature, saturation pressure. Table A3 shows saturation pressure and saturation temperature. So you may wonder which table should I use. In compressed liquid region, the property is a strong function of temperature, not pressure. So we should use table A2. So at 200 degrees Celsius, the compressed liquid may be approximated by the saturated liquid. So entropy for the saturated liquid is 2.3309 kJ per kilogram Kelvin. Do not determine the entropy based on the pressure. The thermodynamic properties are also shown in temperature entropy diagram or TS diagram and enthalpy entropy diagram or HS diagram. So HS diagram is also called a Mollier diagram. This is Mollier diagram. So these diagrams are useful as they visualize the change in thermodynamic property. So on TS diagram, we have a vapor dome, and this is saturated liquid line and saturated vapor line. And we have constant pressure and another constant pressure and constant enthalpy line. On Mollier diagram, y-axis enthalpy, x-axis entropy. This is saturated liquid line, and this is saturated vapor line. So the critical point is here. On the other hand, on TS diagram, critical points at the top of the vapor dome. And this is constant pressure line. We have constant temperature line. So we are not using these tables to retrieve thermodynamic data, but it will be useful to visualize the state